Good afternoon. Welcome to the Mind of STEM channel, where you get your daily dose of science, technology, engineering, and math. My name is Leon Jones, and in this segment, I'm going to talk about the science of fluid mechanics. Now, if you are a mechanical engineer, a civil engineer, a chemical engineer, an aeronautical engineer, an industrial engineer, although industrial engineering you don't deal much with fluid mechanics, an environmental engineer, you deal a lot with fluid mechanics. And the reason why you deal with fluid mechanics is because you want to talk about velocity, flow rate, and you're dealing with fluids. Now, when I talk about the science of fluid mechanics, what is it? Well, fluid mechanics is a branch of physics concerned with the mechanics of fluids. And your fluids are gases, liquids, and plasmas, and the forces on them. It has applications in a wide range of disciplines, including, again, mechanical, civil, biomechanical engineering or biomedical engineering, geophysics, oceanography, meteorology, astrophysics, and biology. Now, fluid mechanics can be divided into two categories. And the two categories are fluid statics, and when something is static, it's at rest. And there's fluid dynamics. If something is dynamic, it is in motion. It is a branch of continuum mechanics, a subject which models matter without using the information that is made out of atoms. That is, it models matter from a macroscopic viewpoint rather than a microscopic viewpoint. Fluid mechanics, especially fluid dynamics, is an active field of research, typically mathematically complex. Many problems are partly or wholly unsolved and are best addressed by numerical methods, typically by using computers. Now, a modern discipline called computational fluid dynamics, again, that's computational fluid dynamics, known as CFD, is devoted to the approach. And the approach is utilizing computers and numerical methods. Now, particle image velocimetry, which is an experimental method for visualizing and analyzing fluid flow, also takes advantage of the highly visual nature of fluid flow. Now, a brief history. The study of fluid mechanics goes back to the days of ancient Greece, when Archimedes investigated fluid statics and buoyancy and formulated this famous law known as the Archimedes principle, which was published in his work on floating bodies, generally to be the first major work on fluid mechanics. Rapid advancement in fluid mechanics began with Leonardo da Vinci, observations and experiments. Evangelista Torricelli invented the barometer. Now, the barometer measures moisture. Isaac Newton, investigated viscosity, and Blaise Pascal researched hydrostatics, and he formulated Pascal's law, and was continued by Daniel Bernoulli with the introduction of mathematical fluid dynamics and hydrodynamica. Now, viscid flow was further analyzed by various mathematicians: Jean Le Rond d'Alembert, Joseph Louis Lagrange, Pierre Simon Laplace, Simeon Denis Poisson, and viscous flow was explored by a multitude of engineers, including Jean Leonard Marie Pussewell and Gottlob Hagen. Now, further mathematical justification was provided by Claude Louis Navier and George Gabriel Stokes in the Navier-Stokes equations and boundary layers were investigated. Ludwig Prandtl, Theodore van Karman, while various scientists such as Osborne, Reynolds, and Andre Cullomgrove and Jeffrey Ingram Taylor advanced the understanding of fluid viscosity and turbulence. Now, again, as I discussed to you earlier, the main branches of fluid mechanics are fluid statics and fluid dynamics. Now, when it comes to fluid statics or hydrostatics, it's the branch of fluid mechanics that studies fluids at rest. It embraces the study of the conditions which fluids are at rest in stable equilibrium, and it is contrasted with fluid dynamics, the study of fluids in motion. Now, hydrostatics offers physical explanations for many phenomena of everyday life, such as why atmospheric pressure changes with altitude, why wood and oil float on water, why the surface of water is always level, whatever the shape of its container. Hydrostatics is a fundamental to hydraulics, the engineering of equipment for storing, transporting, and using fluids. It is also relevant to some aspects of geophysics and astrophysics, for example, in understanding plate tectonics and anomalies in the Earth's gravitational field. Now, to meteorology, to medicine, in the context of studying blood pressure, and many other fields. On the flip side, you have fluid dynamics. It is a subdiscipline of fluid mechanics that deals with fluid flow, the science of liquids and gases in motion. Fluid dynamics offers a systematic structure under these practical disciplines that embraces empirical and semi-empirical laws derived from fluid measurement used to solve practical problems. Now, the solution to a fluid dynamics problem typically involves calculating various properties of the fluid, such as velocity, pressure, density, and temperature, and functions of space and time. Now, it has several disciplines itself, including aerodynamics, the study of air and other gases in motion, and hydrodynamics, the study of liquids in motion. Fluid dynamics has a wide range of applications, including calculating forces and movements on aircraft, determining the mass flow rate of petroleum through pipelines, predicting evolving weather patterns, understanding nebulae and interstellar space, and modeling explosions. Some fluid dynamical principles are also used in traffic engineering and crowd dynamics. Now, again, when we talk about fluids, we talk about flow, whether it's static or whether it is in motion. Now, there are a few equations like the Bernoulli equation. There's also the pressure equation. You have to understand true pressure. You have to understand atmospheric pressure when we deal with fluids. There are calculations that are involved with giving you the formula. Now, again, fluid mechanics is not an easy course. You have to understand differential equations. You have to understand calculus. You have to understand units. Now, when it comes to fluids, a Newtonian fluid, which was named after Sir Isaac Newton, is defined to be a fluid whose shear stress is linearly proportional to the velocity gradient in the direction perpendicular to the plane of shear. The definition means regardless of the forces acting on a fluid, it continues to flow. Now, for example, water is a Newtonian fluid because it continues to display fluid properties no matter how much it is stirred or mixed. A slightly less rigorous definition of a drag or of a small object being moved slowly through the fluid is proportional to the force applied to the object. Compare friction. Important fluids, like water, as well as most gases, to be approximation as a Newtonian fluid under normal conditions on Earth. By contrast, stirring a non-Newtonian fluid can leave a hole behind. This will gradually fill up over time. This behavior is seen in materials such as pudding, oblek, or sand, although sand isn't strictly a fluid. Alternately, stirring a non-Newtonian fluid can cause the viscosity to decrease, so the fluid appears thinner. This is seen in non-drip paints. There are many types of non-Newtonian fluids, as they are defined to be something that fails to obey a particular property. For example, most fluids with long molecular chains can react in a non-Newtonian manner. That concludes this video on the science of fluid mechanics. If you like what I just presented, please comment, share, and subscribe. Also, like the videos. You can also check out the more controversial content on the 411 Talk Zone radio show. Also, if you want to go in depth, have a Blog Talk radio show. Here's every weekend. Now, if you can't find me on YouTube or Blog Talk Radio, simply check out my Facebook and Twitter pages. Once again, thank you for viewing this video on the science of fluid mechanics. Till next time, my name is Leon Jones. Please have a wonderful and gracious day. And remember, you are listening to the Mind of STEM channel, where I give you a daily dose of science, technology, engineering, and math.